Transformations. We've already covered dilations where figure changes size, smaller or larger. So these are the isometric transformations. They do not change size, whereas they may flip or turn or something like that. And I believe those are the words you are used to using in describing some of these transformations. I will be using what's called patty paper, tracing paper, parchment paper. This is small. It's what really comes between your hamburger patties, your meat, but when it's cooked. And I'm also going to have a sample grid so that we can practice and see what happens to these points when we turn them and things. All right, let's begin. Translate. Now, you know what that is. It's just to move it. Sometimes it is called a slide or even a glide, right? Doesn't change orientation. It's still facing the same way. It's just in a different location of the graph. So for example, if we take these 3 points and I ask you to translate by moving left 15 and leave the y alone. Well, left 15 is the x, so I would be subtracting 15 from each of these and not moving the y. So that would leave, I was going to get a pen, we could see this, negative 12, 9 stays the same. 3 minus 15, negative 12 again, the 4 stays the same. 11 minus 15, negative 4, positive 4. So there's your translation. Notice we went from A to A prime, single move. Now this one says go back to the original points, don't use the new ones, and now do sort of a double move. You're going to go right 4, down 6. So plus 4, down 6, all the way across. That's where we get 7 and 3. Remember, plus 4 minus 6, all the way across. 7, negative 2, 15, negative 2. Rotating, it's often called a turn, but remember there are 2 ways to turn. You could take something and turn it left or right. So we've got to make a choice. Well, for some reason, left, counterclockwise is always preferred. So if it doesn't say go clockwise to the right, you will go left, counterclockwise. All right, let's see what happens to our point P. All right, it's at 2, 1. Well, if you're going to use tracing paper, then you're going to need to kind of sketch the axis. Otherwise, you won't know where to stop turning. All right, so there is P. Oh, I'm so sorry. I didn't look up. Now, I want to turn it 90 degrees counterclockwise. That's to the left. So I hold it at the center. Notice it should click into place where the axis line up. And you can see point P is over here. It is at negative 1, positive 2 now. Negative, whoops. Negative 1, positive 2. So what rule is that? Okay, according to the changes here, it looks like they switched. The X and the Y switched locations, and the Y changed its sign. So it looks like this for a rule. Okay, that negative sign does not mean make the Y negative. Make it opposite. So if it's negative, make it positive. If it's positive, make it negative. okay? All right, let's look at 2 turns. I'm gonna line my point back up in the original position. 2 turns. 1, 2, 180. Now I could have gone either way and I'm gonna end up in the same spot. It looks like I'm at -2, +1. I'm sorry, -2, -1. The rule looks like they stayed in the same place, but they both changed their signs. Opposite X, opposite Y. All right, start over, line it up again. And I want 3 turns to the left. 1, 2, and 3. You can see it's here at 1, -2. Okay, this again looks like the X and Y changed locations, but this time the X changed its value. The Y opposite X. Let's just do a practice problem. I could get out patty paper and a grid and do this, or I can apply the rule. 270 is right here. It says flip them around and change the sign of the X. So if I flip them around, I have 10, -8, but I need to change the sign of the X. It was negative, now it is positive. Reflection, that's also called a flip. The orientation reverses like a mirror. Oops, that's an R. Like looking in the mirror. Now up here, orientation changes. If it was a smiley face, it would go sideways. The eyes would be in a different location. This one, you may not be able to tell it changed because if like it's a smiley face, it would be just flipped over. All right, let's see what happens in a flip. We're going to go over the x-axis first. All right, so here is my original. Here is the x-axis. I just flip it over the x-axis, which is turning my paper over. There it is. So it is 2, but -1. It looks like the rule here, they didn't flip, but the Y changes its sign. Remember, it doesn't become negative, it becomes opposite of what it was. You can probably guess what's going to happen with the Y, but let's demonstrate just to make sure. Oh, it would help if I would draw there. All right. Going over the y-axis is side to side like this. So you can see the point is at -2, +1. All right, the rule, they did not flip locations, but the sign of the X changed. The Y remained the same. Now, do you remember where this line is? I know it's been a while since you've had Algebra 1. The Y equals X line, right? If Y is 1, X is 1, 2, 2, 3, 3, -1, -1. You get the picture. 1, 1, 2, 2, 3, 3, -1. You get it. It's the diagonal, right? I want to flip P across the diagonal. That's a little harder to visualize, so we'll just give it a shot here. I am going to attempt to sketch there. Here's my Y equals X line, and I want to fold it across that line. I have to line up my axes as well. There you go. It went straight across. If I was to connect these two, you could see they would be perpendicular, right? All right, this is over 1, up 2. Over 1, up 2. Oh, what happened? They just reversed location. Nobody changed a sign. All right, let's give it a shot here. We have the same point we had, but it's reflected over the x-axis. I'm using this rule. All right, they stay in the same location. I'm going to have -8, 10, but I need to change the sign of the y. There we go. -8, -10 is the new place. All right, a shape can have reflectional symmetry. In other words, where can I fold the shape and it matches exactly on both halves? For example, we have a beautiful little heart. Now, where can I fold this? And most all of you would tell me right down the middle. Well, that's the good thing about patty paper. Looky there. If I folded it, well, my drawing is not straight, but you can tell the picture matched up perfectly. So that is a line of symmetry. It would be like I could hold the mirror up to one part and it would match through the mirror on the other side. I often have people ask, can we fold it from top to bottom? Well, just in case you're not sure, you grab a piece of paper and you try it, and then you go, oh, no, that didn't work. Diagonals, nope, don't work. So I think we're done. It has one line of symmetry. I don't know what happened to my copy here. That's supposed to be filled in. All right, where can I fold this shape? Well, I'm just going to kind of sketch the outside of it, and then I've got this right here. I think most everybody would say you could fold it right here. Well, let's find out. Yep, if I could draw straight, you can see it does match up. Can I fold it this way? Right here? Well, let's find out. Yeah, if I could fold straight, sure can. So it will have two lines of symmetry that are perpendicular to each other. Can't fold it this way though, because of that bar in the center. All right, let's look at the parallelogram. Sometimes the wax prevents a pen from drawing on here very well. So. All right, top to bottom, horizontally. No, that does not work. Side to side. No. Diagonally. Oh, definitely not. Well, it has 0 lines of symmetry. I think most everyone can see that if you fold this one right here, you're going to get symmetry. There won't be any diagonal ways to do that one. So we're left with one line of symmetry. Reflectional symmetry is just where can you fold it and it matches up perfectly. Now, rotational symmetry is a little bit different. It asks for turning, okay? So I'm looking for the degrees that I can turn it so that it's exactly the same as what I'm looking at now. How many degrees can I turn it so it looks just like it does now? All right, I'm going to get a new piece of paper. I think I've drawn all over that one. It looks like I have a regular octagon. Remember, regular means all the angles are the same, all the sides are the same. Kind of the perfect version. I'm just going to make one vertex kind of big so I can see. I'm going to hold it center-ish. Well, if I turn it right there, you can see nothing lines up. But if I turn it there, it looks exactly the same. So basically, this corner went to this corner. I could do that for every one of these corners, can't I? Let's double check. 1, yep, 2, 3. I didn't hold it quite in the center, but I could do that for every side. All right, 360 degrees in one full turn divided by the 8 turns that I can get in this picture. That tells you the degree of rotational symmetry. So for one turn, it's 45 degrees. All I did was divide those. 2 turns, 90 degrees, 45 times 2. 3 turns, 135 degrees. 4 turns, well, that would be halfway around. We know that's 180, and we could keep going. So how many degrees of rotational symmetry? 45 per turn, per rotation. What about this guy? Kind of looks like a big red cross symbol. Well, let's find out. My sketch is not perfect, but I think it will do. I'm going to just check with one corner. If I turn it to the other corner, whoa, that did not work. But I can see it's going to line up here. Huh. So this corner turned all the way around to this corner. How many times can you do that? You're right. 4. So 360 divided by 4 turns that I can make. So 1 turn, 90-degree rotational. 2 turn, 180. 3 turns, 270. And then 3 turns, of course, would be back to where we started. So this figure has 90 degrees per turn of rotational symmetry. All right, what about this little odd looking guy? I don't know till I draw it. Because I mean, it's a circle. Does that mean it has 360 degrees? Well, you could tell I am no good at tracing. Oh, those lines are going to make a difference, aren't they? Ah, so from here, I had to go all the way around to here for one turn. How many times can I do that? Excuse me, turn off my phone. Well, I can only do that 4 times. So it has the same as this one. 90 degrees per turn. On the back side is a U trisection. I want you to do these right now, and then we're going to talk about them, okay?